Hi, everyone. Thank you for joining. I'm grateful for your time, and it's great to be here in this virtual sense at DataFest 2020. Today, I'm going to be talking to you about what I think is probably the next big thing, if you like, in data analytics and AI, or certainly one among many, and that's causal inference and causal reasoning. And I'll do that on the occasion of our open source tool called CausalNex, which I'm going to also demo later in the session. I'm representing Quantum Black, which is part of McKinsey and Company. And it's a data analytics firm within McKinsey. It was born out of the wonderful world of Formula One, and has grown to be one of the biggest service providers in the space of advanced analytics worldwide, operating across pretty much every big industrial domain, to name but a few: healthcare, elite sport, financial services, telecommunications, marketing, and media. It's a great privilege to be part of this team. I joined recently. My own background is mixed from academia. I was a lecturer at Imperial College for a while. I still maintain an honorary affiliation there. And I also spent a few years consulting in industry, and also a few years as head of research departments in large technology organizations. And what I'll be presenting here is indeed a research project, or the outcome of one. So it's an interesting insight into how a very large historic organization like McKinsey maintains an edge in the space of advanced analytics via the use of open source and published research, and a reliance on the community. So we're particularly grateful for your attention today, and hope to turn this into the start of a long conversation via our open source engagement. So there's a number of areas in which we have invested efforts in research and development in the past, and I'm going to name a few here so that I can segue into our work in causality. We're interested in fairness and bias, and in general ethics in data science. That's a growing area resulting from the fact that data science and AI are maturing as technologies, and their impact is extremely broad. And as a result, there's potential for harm whenever a technology has such impact. Part of that, and related to that, is an attempt to make AI accountable, to make it explainable, so that we can both better understand what an AI system is likely to do in any given situation, but also to ensure that the users and the stakeholders in an AI system have the capacity to reason about the role that the AI is playing in their lives in a human interpretable way. Some other areas that I'm not going to mention a lot about are reinforcement learning and deep learning, and obviously we're investing in these areas as well, and live model performance tracking, so tracking how well a model does after it's been deployed. All of these are very important, but today I'm going to focus on causal inference, which is related to explainability and indeed to fairness, as I'm going to mention in passing later on. And causal inference can be summarized as the attempt to extract causal relationships as opposed to just correlations from data. And this relies on a number of different techniques, but primarily in the case of a consulting project, it would entail very deep integration of domain expert insights. So insights that one could acquire by interviewing, for example, a domain expert. And these are very seamlessly brought into the model, into the machine learning model, via the toolbox of causal inference. Now, I want to double down on my comment about explainability. I think it's extremely important to develop explainable machine learning methods, because explainability is the stepping stone towards trust. And without trust, there are very strong limitations on what a technology can achieve in society as a whole. I think that as a data scientist in the modern environment, one has to be conversant with a very large number of techniques. And each of these techniques will have a different profile with regards to its explainability. So a big amount of effort into the space of explainability is invested in what we call post hoc XAI, explainable AI, which involves wrappers around existing machine learning models that offer simple explanations of their behavior, so that, for example, a deep neural net can be interpreted by a human, despite the huge number of parameters that it entails. Now, one layer down in this pyramid, there's models that are intrinsically interpretable. So they're simple enough that their parameters can, for any given use case and data set, attain real-world meaning. So a classical example would be linear regression or logistic regression or that family of generalized linear regressions, where the parameter itself represents the effect one variable has on another variable. And it's been used massively in many domains over the last 60, 70 years. One level even further down from that is called causal inference, where the attempt is to capture not just effects that represent correlations, so observed cohesion between outcomes, but rather causation, so mechanistic relationships between variables that have consequences in terms of what would happen if we change the value of one variable. So they have counterfactual validity, which is a very strong form of generalizability. There are a number of approaches in the academic literature on causal inference, and I should have mentioned earlier, my background is as a statistician, although I also have a computer science background. And in statistics, in areas such as econometrics and obviously epidemiology, we have struggled for decades to get our heads around what it means to infer causation from data. And the best answer that we ended up with is the format of a doubly blind or otherwise randomized clinical trial, where the effect that we're trying to discover is assessed by means of randomly assigning a subject in the study to one treatment versus another. And by virtue of that random assignment, we can ensure that the fact that a certain subject took the treatment is independent of any outcome that the treatment might cause. And in that way, we can generate a causal conclusion. However, randomized experiments are not always possible in other domains. For example, in situations where there are ethical considerations that preclude the running of a randomized experiment, or in situations where we're trying to look back retrospectively to data that have already been collected, otherwise known as observational data. So this is the niche in which we're going to focus, the attempt to extract or build upon causal knowledge in observational data. That's the topic of today's presentation. So taking a step back for a moment, it's interesting to consider how different ways of splitting data science and machine learning into categories can be helpful in reasoning about causality. A common way is to talk of predictive, descriptive, and prescriptive modeling. Predictive modeling is pretty much the bulk of modern data science. So the idea there is that you're observing certain patterns in historical data that you try to extrapolate from for future data. And therefore, you're basically discovering, using data, a relationship between X, which is a description of, say, an object that you want to classify, for example, an image. That could be X, and F would be a very complex nonlinear function that maps X images onto spaces of labels, for example, cats or dogs being a classical overused example. So in predictive modeling, what we care about is how accurate our predictions Y are when compared to real data. And this means that in the presence of labeled data, we can automate a lot of the standard pipeline of a predictive model. And that explains recent trends like AutoML, for example, this reliance on Y. It's a very sort of human-free problem. In a sense, the human is only involved insofar as they generate the labels. And then the training of the model and the extraction of the insights, in this case predictions, is automatic via algorithmic techniques. The next category is often known as explanatory modeling and sometimes confused with descriptive modeling. I'm going to talk about that in a second. Explanatory modeling and descriptive modeling alike are focused on describing the relationship itself. So if we can find a mapping from X to Y that is pretty accurate, so there is some element of predictive accuracy always present in everything we do, but getting the best possible prediction is not our end objective here. Instead, we want to be able to tell a story about what it is about X that made us think that its label should be Y. Classical example is, again, the example of a pharmaceutical clinical trial where we're trying to identify what effect precisely and how an effect is mediated by by giving a drug to a patient. So descriptive versus explanatory in this particular literature tends to, again, relate to causality. So descriptive modeling is basically a description of what we see, the patterns that we observe, without making any counterfactual claim. So descriptive modeling won't actually tell you what would happen if the data were different. It's just telling you what happens in the data that we have. Explanatory modeling, the term explanation in the philosophy of science, is usually associated with a much stronger type of knowledge, which is causal knowledge. And causal knowledge is exactly what I've been talking about in terms of counterfactual validity. It's the type of knowledge that will persist even if you intervene and manually change one of the values in your input. And that relates, of course, to prescriptive modeling. So a lot of optimization relies on a known F. So you know the relationship and you want to identify the value of X that maximizes Y. But in the instance where F is not known, then optimization and in general optimizing actions and interventions, so prescriptive modeling, does rely on a representation of the relationship that is very strongly true in that counterfactual sense, in that you will then step in and change the values of the variable. And you want to ensure that the mapping that you've learned persists under that type of action. So we're going to talk more about this in a second. But it's always good to work on the basis of an example. So let's consider this plot on the left where we are plotting forest fires against the month of the year and also ice cream and its sales against the month of the year. And you can see that there's a pretty strong, nearly perfect correlation between these two variables. And yet anybody would immediately be able to tell you that there is no causal link flowing from one or the other variable here. It's impossible that ice cream could be causing a forest fire or vice versa. Indeed, what's happening here is that there's a common variable to both, a common cause, which is temperature. So in this instance, we observe that an explanatory model would like to have a complete narrative. It would like to have the value of temperature at play rather than report a strong correlation between these two variables on their own. And the reason is that if, let's say, you were an alien that lands on planet Earth and knows nothing about what ice cream is, you might be tempted from this analysis to think that if you force somehow additional sales of ice cream, say by lowering the price of ice cream, then you can cause forest fires, or conversely, by banning ice cream, you can stop the problem of forest fires. And clearly that's not true because the relationship is mediated by a common cause. It's not directly causal. And similarly, you can see that the weight of the average person in a country tends to fall during the summer period for aesthetic reasons, but ice cream tends to grow in sales. And again, one could conclude from this chart that ice cream is a diet food. So these examples are silly because our human intellect is immediately able to tell that the causal relationship which is implied by them couldn't possibly be true. And that's because we have context that is not present in the data. But in cases where that context and that domain expertise is either harder to get because it requires 20 years of medical training, for example, or even absent in areas where science hasn't yet figured out the flows of causality, then we're in danger if we're using predictive modeling for explanatory purposes. So yet another example is the following, and here we want to get just a little bit more technical. We're going to apply a linear regression to a number of variables, including country of residence, type of car owned, age, exposure to sun, and illness. And it is quite clear that exposure to sun will be a factor, risk factor for illness, as well as age. It's much less clear that the country of residence should be directly related to illness, and certainly the type of car owned shouldn't. And what's interesting here is that if we fit a linear regression on a model that only contains exposure to sun, then of course we get a fairly high coefficient of 0.99. The model has a pretty strong opinion that the two variables are related. Now, if we additionally add car to that, which should have been independent because we don't suspect any mechanistic connection between having a car and what type of car you have and falling ill with something like skin cancer. Well, in that case, however, adding car reverses the coefficient that represents the correlation between exposure to sun and illness to a -1. Now, that is not a surprise to a trained statistician, but if you report that finding to a domain analyst or to a client, they will have a very, very hard time understanding what's going on. This is related to what is known as a Simpson paradox. And the idea is that by adding the type of car, you have now leaked some information about the age of the individual. And in doing that, you have managed to change the residual relationship between exposure to sun and illness. So linear regression can be interpreted with care along causal dimensions, but it requires quite complex arguments to do so. So let's drill into why that is the case. Let's go back to our example of forest fires and ice cream sales. Now, as we discussed, really what's happening here is that there's a common cause, which we represent here as temperature. And if we don't observe that, then that creates correlation between forest fires and ice cream sales. But if we do, conditionally on temperature, forest fires and ice cream sales are uncorrelated. Another way to think about this is that for any given value of the temperature, so if we condition literally on the temperature, or if we observe the temperature, then forest fires and ice cream sales will be uncorrelated within that bin of values, say, for temperature. So if we only look at the month of June, then it's unlikely that there's still going to be a correlation or as strong a correlation between forest fires and ice cream sales. Now, that suggests that if we include all possible common causes, which is the technical term for a confounder, then we might be able to remove the problem and continue to use simple techniques like linear regression as long as we include all possible confounders. And indeed, that's the advice that we give to junior statisticians or junior data scientists. Look for confounders. But there's another way for us to get it wrong, and that's to condition on possible colliders. A collider is a downstream effect which is simultaneously caused by two variables of interest. And there are several examples of this. It's known as Bergson's paradox in the history of statistics and data science. But a more amusing recasting of this paradox was featured in Slate magazine, known as the notorious article on why handsome men tend to be jerks, excuse the language. And the idea here is that there is a variable which is not observed, which is not focused on rather, which is whether a given individual would date a person. And for somebody to date a man, then we could simplistically say that man should either have good looks or be caring, right? If it's both, then even better. But for someone who's very rude and nasty, to make it to the dating pool, they need to be comparatively better looking. And conversely, for somebody who doesn't have looks on their side, perhaps being nicer and then more polite might be enough to get them into the dating pool. And as a result, if we look at the dating pool, disregarding the fact that there's this selection bias, good looks will be negatively correlated with caringness. Of course, in the broader population, we don't know that to be the case. There's no reason why, say, genetically, these two traits should be negatively correlated. So then in order to have a clear picture when we're looking at simple techniques like linear regression, we need to make sure that we include all possible confounders, but not condition on any possible colliders. But then what about children of colliders, or confounders of children of colliders, or colliders of children? So you can see how that structure becomes exponentially difficult to reason with. So fundamentally what we need to do is we need a graph, right? We cannot list confounders and colliders and know what we have to do just on the basis of these lists of variables. We need to understand how they are interrelated, and that is best represented as a graph. So that's what a Bayesian network is, right? We go from a simple representation of the regression, effectively, of the variable of interest to a bunch of features, which is the standard machine learning paradigm, to a full rich representation of the dependencies and causal mechanisms between all variables. So relationships between features and the response, sure, but also relationships between the features themselves. So by capturing all of these relationships faithfully, we can then be sure that no matter what we're observing or conditioning on, our answers will be valid, and we won't be drawn into Bergson-type paradoxes. CausalNex then is a tool that uses Bayesian networks as a representation of causal relationships. Now, it's worth saying that Bayesian networks are not necessarily causal. They're only causal when we have good grounds to believe that the arrows present in the graph represent true causal relationships. So there is a lot of literature on Bayesian networks used as an observational tool where there is no presumption of causal relationships. And I'll get back to that question of how do we differentiate between an edge which is causal versus one which is not in a second. But fundamentally, as a data structure, Bayesian network is a very efficient way to represent causal mechanisms and correlation structures alike. Now, this brings us to CausalNex. We were finding ourselves having to use causal inference very often in our projects. After all, most of our projects aim at generating actionable insights, and the word actionable is referring to precisely that counterfactual validity, that one could act upon an observed pattern so that a certain outcome may be achieved. Another word frequently used in consulting is drivers of performance. Again, the implied meaning of a driver is that you could use it as a lever, that if you change its value, it will favorably change the outcome. So we were finding ourselves using that type of technology so often that we pulled together our best practices and filled what we think is a bit of a gap in the open source software community for Python in creating CausalNex. And you can, and I encourage you to all visit CausalNex on GitHub. It's also available on PyPy, and follow us, star us, and watch us for more updates in the future. So what does CausalNex do? Well, we've already said it leverages Bayesian networks, but how does it do that? So I mentioned before that Bayesian networks by themselves are basically a data structure and a mathematical tool. They don't have magic powers, so they cannot discover causal relationships for free and tell them apart from correlations. But what they can do is invite the human expert to specify causal relationships that they know in advance, or rule out causal relationships that they think are extremely unlikely. And the graphical representation of that probability distribution effectively is what allows this very rich interaction between the human and the machine. We rely on that rich visual representation of a graph. So visualization is important in this context, and indeed CausalNex supports advanced visualization techniques for graphs. Now, once the structure has been determined by a combination of data-driven techniques that I'm going to talk about in a second, and parameter estimation and human, data-driven techniques and human knowledge, then we move to parameter estimation, which is in effect the exercise of identifying exactly how strong the correlations and the causal relationships that we presupposed exist in the data are. And that can occur via standard approaches like maximum likelihood or Bayesian inference. Finally, once the data structure is complete with both edges and weights on these edges, we can run any counterfactual analysis we want. So recall, we are representing the full multivariate distribution, so there is no constraint as to which one is the target variable. We can choose to condition any of the variables in our graph, observe another subset of them, and predict the remainders. So it's a very flexible API, a very flexible interface for queries on this object that represents our knowledge about the system, complete with human expertise and data. So going in a bit more detail, the steps that we follow are, to start with, we populate the graph with a good candidate structure dictated by correlations alone, right? So we're going to do a structural discovery step. And for a very large number of variables, this step is quite crucial. And it was indeed one of the bottlenecks of the adoption of Bayes nets historically, because first of all, it's a combinatorially hard problem, right? So you need to search over all possible graphs, and we all know or can suspect that this is a very large set. But secondly, if you don't have somewhere to start from and you get the expert and start asking them questions about hundreds of variables and their relationships, they get swamped. Instead, what we want is to start with a good candidate supported by the data, and then embed domain expertise, which is the second step. So the expert can inspect the graph and they can argue that certain arrows are missing, whereas they should be present because they know there's a direct causal relationship there, or certain arrows make no sense because there is no way in which these two variables could be causally connected. So that's how the expert starts having a conversation with the data scientist mediated by the graph that has been discovered in the first step. Visualization, therefore, is very important in these two steps. Once that's set, once that's decided, then we move to likelihood estimation, which involves estimating the actual values of the strengths of these correlations. The end product is a full likelihood, or if you like, probability distribution over the variables in question. And finally, we can then query that object counterfactually in any way we like. So the representation of the graph that we use is a directed acyclic graph. So it's directed in the sense that there's the arrows are pointing in a certain way, and that direction reflects the causal flow, or at least we intended to reflect that. And it's acyclic in the sense that we don't allow any loops. So it's not possible to start from a variable and following the edges along their direction, go around the graph and come back to the same variable, because causality doesn't work like that. That's the high level abstract reason. There's also technical reasons why that's not allowed. So nodes represent variables, edges represent primarily causal relationships, but there's also a statistical interpretation, which is that the value of a node should be independent of the rest of the variables in the graph, given its parents. So that's the statistical interpretation of a Bayesian network, whereas the causal one is a little bit more straightforward in that B has to at least partially influence A. Now, let's talk briefly about how we do structural discovery. So there's several learning methodologies. One is to fully rely on the expert, which doesn't scale very well, as we discussed. So we're looking for hybrid approaches here. Then at the other extreme, there's the constraint-based approach, where each individual arrow or each combination of ours is ascertained from the data using effectively testing, hypothesis testing, or something similar, Bayesian equivalent, for example, like slab and spike methods. And this is also tends to be quite slow for frankly the same reason, because each edge is pretty much interrogated by itself. There's a faster way to get to structures that are good candidates, and that's score-based techniques. So basically optimization-based techniques, where we define a score that hopefully is a good approximation to our combinatorial search problem. And that score will in general tend to penalize structures that don't fit the data well and favor structures that fit the data better. And then we optimize that score using some gradient-based techniques or other type of optimization algorithm. And that's the flavor that we have gone for in CausalNex. We implemented a paper called DAGs with no tears by Zheng et al. We were luckily able to be in contact with the authors, and we were impressed with the performance of the algorithm. So we decided to go for that on the back end of CausalNex. Now, no tears is a score-based method, and the trick that it uses, if you like, is that it creates an objective function, which takes advantage of a certain fact about adjacency matrices. Adjacency matrices are matrices that represent the connections between edges, between nodes on a graph, and they have a very nice property, which is that if you apply them to themselves, so if you take the product of two adjacency matrices, that's the same as taking sort of two-step journeys along the graph. So whereas a simple adjacency matrix describes where you can go to in one step from each location of the graph, that matrix to the power of 2 represents where you can go in 2 steps, and so on. So we can make a mathematical observation that as we increase the powers of that graph, that starts to look like an expansion of an exponential operation. And on that basis, we're able to define a simple to state, mathematically simple to state score, which tries to enforce that the diagonal entries, which is the ability to go from one node to itself of all the powers of this matrix, are 0. So basically, that would mean in practice that it's impossible to go from A back to A in 1, 2, 3, and so on, as many steps as you can try. It's still impossible. And that's the idea behind the mathematics. And the way that we penalize that behavior is by using what is known as L1 regularization. So whereas most classical optimization algorithms depend on L2 or sort of continuous differentiable scores like L2, which is squared difference. L1, which is the absolute difference, is actually not differentiable at 0, and that corner, which is created like a V sign, you can think of it, at 0, creates a local sort of discontinuity in the derivative. That means that solutions that are exactly 0 are actually favored. It's a pretty magical observation made popular by the Lasso algorithm in regression, but hence used across the board in many interesting optimization problems of that nature. So it basically is a technique that recasts a combinatorial problem into a continuous optimization problem, into a convex problem. Now, once we have a good candidate structure, we then involve the expert, and that's how we can guarantee that the best possible causal knowledge available to us is captured in the representation. A good example, which relates back to the fairness and ethics in AI angle that I mentioned in the beginning, is the one on the right-hand side. So here we have 3 edges that point from the grade of somebody and the address and the access to internet of somebody to their gender. We know that none of these could possibly be influencing gender. They are most likely, these correlations are introduced by other confounding or colliding variables. More generally, we can very successfully represent assumptions about fairness causally. Actually, that is what they mean if you think about it quite carefully. A fairness assumption is saying that gender or other protected attributes could not possibly be causing by themselves a drop in performance on any area, such as grades or job performance. And as a result, by banning these direct links, we can force the optimization method to look for explanations in that, in possibly observed differences in performance to other variables like socioeconomic status or other variables that can explain away any observed differences and not attribute them falsely to gender just because our set of variables is incomplete. So the human expert can then have very, very deep insight captured in this graph by virtue of either banning edges or flipping their direction or introducing edges. And following that, we're now in a position to learn the parameters. Now, some technical remarks that I'm not going to spend too much time on involve the use of discretization. So Bayesian networks in the classical literature are mostly either fully discrete. This is probably the most classical example of Bayesian networks, or fully Gaussian, and that would be often called a Gaussian graphical model, GGM, or Gaussian graphical network. The reason why discrete distributions or altogether Gaussian distributions are preferred is because of closure properties. So if you have a number of variables and each of them is discrete, then the whole of them together can be dealt with using conditional probability tables, and they're all sort of jointly multinomial random variables. Analogously, Gaussian variables play very well with each other. Like you can condition on one of two Gaussian variables, and then the conditional distribution is also Gaussian. You can marginalize one away, and the marginal is also Gaussian. So any operation that you might need to take over the graphical network, the Bayesian network, will preserve the distributional shape. So it will keep you within the same family of distributions. Now, we're very much aware of the limitations that this poses, and we're working on non-parametric versions of Bayesian networks that do allow you to work flexibly across different types of distributions and don't make the strong assumptions that Gaussianity does. But if we had to pick between Gaussian and discrete, we have decided to go with discrete because despite the obvious discretization error, at least you're able to capture oddly shaped distributions, whereas with a Gaussian, you're not. Here's an example of an oddly shaped distribution, and there's many ways in which you can discretize it, and that is also something that you work on with the expert. So it's a bit more flexible. So then what is a conditional probability distribution or a conditional probability table? Well, that's basically what lies beneath a graphical structure. So the structure tells you what the causal relationships are. And then for each of those relationships, you need to specify what the probability of attaining a certain state for any given variable is, given the states of the parent nodes, right? So basically the size of a conditional probability table, and you have one of those for each node in the graph, their size depends on the number of states that the child variable has multiplied by the product of the number of the parent states. And for the whole graph, then you need to consider all such parent-children relationships to understand the size of the graph, the number of parameters that you need to estimate from data. As a general rule, the whole thing scales with the most connected subgraph of the graph that you have. So if you have a child node with many states and many parents, then that will dominate the computational complexity of the algorithm. Finally, once you have determined what the parameters to be estimated are, then you have to actually estimate them. And you can either use maximum likelihood estimation, which is effectively a gradient descent on the likelihood, and it will result in a point estimate. So just a single value for each parameter in the conditional probability table, or confidence interval at best. You can also do Bayesian estimation, which involves putting prior beliefs on each of these strengths. So it allows for even further encoding of human expertise in the form of prior beliefs about the strengths of the associations, not just the directions and the presence of them. and that has, in the case of discrete random variables, a very nice representation. It boils down to assuming pseudo counts. So basically pretending that we have already observed certain data of a certain type. So it's, again, a very nice closure property. And given the variables of interest are actually either binary or discrete, we can assess the performance of our methods using standard classification scores. We can pick a target, and remember, we can really do pick one. We don't have to decide what the target is in advance, like in most classical machine learning. We're here representing all possible relationships, so we can decide to produce, for example, a classification score for each variable in our set. And here we're presenting a ROC curve, receiver operating characteristic curve, which basically shows you how the classifier trades off false positives with false negatives. And the area under the curve is often a metric that we can use to summarize performance, predictive performance effectively on each variable of our graphical network. So I want to end that section of the talk by just giving you a bit of insight into the different kinds of queries and operations we can apply to Bayesian networks. Let's consider this simple schematic where A is a common cause of B and C, and C is also influenced by B. So even after taking into account the effect of A on C, B still has something to say about it. So this is unlike the example of a forest fire and ice cream where temperature was the only common cause. Here we have an example where B still plays a role. So for example, it could be how dry a certain part of the forest is. The dryness, the aridity, is a function of temperature, but even if we take temperature into account, it's still the case that on any given hot day, a drier, more arid forest batch will be more likely to burn than not. And finally, we have a child D that only depends on B. So let's assume that we're interested in C in this example. Now, if we condition on D, so let's say that we want to assume, we want to only look at the data, at the part of the data where D was true, or in this case, equal to a value D. That will update the whole network, right? Despite the fact that the causal direction goes downstream, the fact that we know anything about D makes different values of B more or less likely, right? So if we know that there was a forest fire, that tells us something about the temperature. It tells us that it's more likely than not that it was a hot day. So knowledge can go upstream, causality can go downstream, and knowledge upstream and narrow in a Gaussian, in a Bayesian network. However, if we intervene and fix the value of D, right? So if we were able to somehow not simply observe D, but rather make it so that D is true, then in that case, there's nothing to update. No knowledge goes upstream in this instance. So the example of forest fires is becoming a bit unfortunate, but I'm still going to run with it because it's illustrative. If somebody actually set a fire to the forest, then that tells us nothing about whether it was a hot day or not. The extent of the fire might, but the fact that there was a fire, if we have somebody set the fire, then that tells us nothing about the rest of the graph. However, if we intervene on B instead, which is nested more deeply into the graph, that will update its children, but it's not going to be the same as conditioning on B, because the intervention does affect its children. So the fact that we didn't observe B to be different, but we actually changed doesn't remove the causal consequences of B, but it does mean that it's not providing us any more information about A, which is a cause of B. Right? So the fact that somebody set fire to the forest tells us a lot about the presence of smoke in the sky, but it doesn't tell us much about temperature. And finally, there are situations that are mixed in the sense that A, which is a root variable, means that it has no parents. A will be having the same information flow on the rest of the network, whether we intervene or observe. And that's because, like I said, when you intervene on a variable or observe it, its consequences remain the same. It's still going to have the causal effects that it's going to have. And there's nothing upstream for us to change our mind about, given what we now know about A. And finally, I just want to make the point that we can also do both, right? We can intervene on one variable whilst observing another. So this is a very rich representation. I should have mentioned from the beginning the meaning of the operator do here, but you might have gathered it from my descriptions. The do operator was introduced by Julius Pearl, who is the inventor of Bayesian networks, but also the inventor of what is turning out to be a very popular framework for causal inference called the do calculus. In his recent book, The Book of Why, is an excellent sort of popular science introduction to the subject. And the do operator is meant to distinguish precisely between the idea of conditioning on an observation that you didn't have anything to do with versus conditioning on an intervention. And like I said, again, that is a key difference, because an intervention has nothing to say about upstream variables, whereas an observation does, because it's giving you evidence of a certain cause having an effect. So I want to wrap up by going quickly through the latest features in CausalNex, and these are the following. So we've now introduced wrappers in CausalNex so that you can use familiar scikit-learn interfaces for regression and classification. That makes its usability much better. And it also means that we're preserving some of the nice interfaces that you know from other classifiers, like feature importances and coefficients of the model can be extracted using the same methods and attributes. But quite strikingly, the technique is very performant because we've been able to introduce non-parametric relationships in our DAGs, and by the use of PyTorch parallelization, we can now scale up to thousands of features, which is a very, very strong result, and it significantly expands the number of use cases that we can cover. In terms of future work, we plan to incorporate many more distribution types. In particular, we want to extend the wrapper for DAG classifier to deal with multiple labels rather than just binary. And we also want to introduce Poisson count data. A Poisson distribution is a very popular choice for modeling counts, and that's something we want to integrate. And we also want to extend the ease of use of the interpretability properties of a DAG, which at the moment you can, of course, make use of with further work, but we want to wrap more of that functionality into the package itself. So the new version is out now, 0.8.0, and we encourage you to give it a shot. Finally, we've also considered dynamic Bayesian networks, which is a version of a Bayesian network that unfolds over time. So as you can see in the example here, the causal relationship is one where x1 influences x3, which then influences x1 at the next time step. This sort of modeling is very important in a number of fields, longitudinal studies in fields ranging from epidemiology to economics, but also obviously sensor networks, financial stocks, you name it. There's many types of data sets that are temporal in that sense, and understanding how causality propagates over time is very important. Of course, that introduces further challenges because some of these parameters have to be shared across time, which makes the optimization problem a little bit more intricate to express mathematically. But it's still possible, and our latest piece of work called DYNOTEARS was a modification and adaptation of the DYNOTEARS algorithm for discovering structures that persist over time in that sense. So this led to a paper in AI stats called DYNOTEARS, structured learning from time series data. But also, happily, we have now merged that feature into CausalNex, and you can now experiment with time series data, multivariate time series data, in addition to static data with CausalNex. So I wanted to thank you again for your attention and emphasize that causality is an area where many institutions and organizations are investing in open source. It's not just us. There's other packages out there that we encourage you to look into. But we do think that there's a shortage of tools despite this renewed interest, and we really welcome any contributions from the community in order for us to be able to finally move beyond what is a very old statistical adage, which is correlation does not imply causation. I think it's time for us to try and move beyond that and embrace representations of causal knowledge in all industries and all domains. Thank you very much for your attention, and we'll have a Q&A session live over video conference soon. Thank you.